Yes, so we are, I think I told you guys that we're doing this in kind of a strange way. Unit 4 has Section 19, Section 20, and Section 21, but there was already a lot of bleeding between Section 19 and Section 20 and 21. When we did nomenclature and we organized reactivity, we're not going to review all of that. We just kind of did that for the whole unit. The only thing that we have left to talk about is how to synthesize carboxylic acids, how to synthesize all of the derivatives, and how all of these different carbonyl groups interchange between each other. And we also have a couple of mechanisms that we're going to be looking at. So I actually want to take us through the mechanisms for the reactions that we saw wrapping up aldehydes and ketones. So the first one I actually want to take us through is the acid and base catalyzed hydrolysis. The hydration of the aldehydes and the ketones. I'm going to keep things simple, and we're just going to look at acetaldehyde, and we'll react it with hydroxide and water to give us 1,1-ethane diol. The reason I want to start here is because it highlights really important trends about being in basic conditions versus acidic conditions. In these basic conditions, and I'm going to actually draw my mechanism here by having each reagent that will have a relevant role drawn throughout the entire thing. You could show just what's necessary at each point. In basic conditions, there's nothing to be protonated. If anything, things might become deprotonated. Since there's not really anything very acidic, we're going to look more at that in Unit 5. The first thing that we should expect to do here is actually some sort of nucleophilic attack. So the nucleophile is going to attack the electrophile, the electrophilic carbonyl. Can either of you tell me why hydroxide attacks the carbonyl and not water? Okay, sorry. Why is it hydroxide attacks the carbonyl rather than water attacking the carbonyl? You have a good point that hydroxide and water couldn't react with themselves, but it would just produce hydroxide and water. Why is it that water is not the nucleophile and hydroxide is? Water's neutral, hydroxide is negative. It's that negative charge makes it more nucleophilic. Think of it as a magnet. That's a very weak magnet being drawn towards a weak magnet. That's a very strong magnet being pulled towards a weak magnet. So it's just strength of the nucleophile there. And you can see that here I've done an addition reaction, so I've opened up my carbonyl, and now in my second step, that negative charge on the oxygen deprotonates water, and I've taken my aldehyde to a diol. What charge do you see consistent throughout the mechanism? The negative charge. So I want you to think in basic conditions, there should be a negative charge throughout the mechanism. Let's be honest, there is a positive charge somewhere. You can't get hydroxide without having potassium ion or sodium ion or ammonium ion. There's something balancing hydroxide. That something is irrelevant. I did do one thing that I want to highlight in the mechanism. I actually forgot to put hydroxide there at the end. That's important because otherwise it wouldn't be catalyzed. Let's take the same acetaldehyde and react it in acidic conditions to see how forming 1,2-ethane 1,1-ethane-diol is different in acidic conditions compared to our basic conditions. In acidic conditions, there's really no strong nucleophile to react with my carbonyl. Instead, the carbonyl becomes the nucleophile. The carbonyl becomes basic in acidic conditions. In basic conditions, the carbonyl is electrophilic. In acidic conditions, the carbonyl is basic. And we reviewed this on the first day of this unit. The most basic part of the carbonyl is the carbonyl oxygen. So the first step is to protonate the carbonyl. By placing that positive on the oxygen, there's now a much stronger resonance form where the carbon also holds a positive charge. What we have just done by protonating the oxygen is we have made the carbonyl more electrophilic than it was before. What was our best nucleophile here? Hydroxide. There's no hydroxide anymore. So because of that, water is not nearly as nucleophilic. It's only going to attack once the carbonyl is protonated. Now that the carbonyl is a better electrophile, water can attack and open the carbonyl. Notice what charge is consistent throughout the acidic conditions. Everything's protonated. Basic or nucleophilic conditions favors a negative charge. Acidic conditions is going to favor a positive charge. Now, because water has just added to the carbonyl, it's still protonated, which means I haven't gotten to my diol yet, and the last step is to see the deprotonation of that second alcohol, which reforms our acid. I'm sorry that I'm kind of cutting it off there and doing a weird angle thing, but I want to use the rest of the board. So, a word to the wise. If you're looking at acidic conditions, it's rare that you should have a negative charge, if ever. In basic conditions, it's rare that you should have a positive charge, if ever. Okay? Now, let's look at the acetal and hemiacetal mechanisms. I'll give you guys a hemiacetal reaction where we just use a compound that has one alcohol. When we do the acetal mechanism, I'll use a diol, a compound that has two alcohols attached. But I want you guys to recognize that it could just as easily be two different equivalences of the same compound. The mechanism doesn't change. What atoms attack in what order doesn't change. What can change is what those atoms are attached to, what molecule they come from. So let's take benzophenone. Let's react it with methanol in acidic conditions. And let's just look for the production of the hemiacetal. Now, H+, I told you guys, is a very challenging reagent to use as a base. So on your unit tests and on your exams, I accept using H+ as TSOH or ACOH. But I would advise not to use H3O+, because that implies aqueous conditions, and the product can be hydrolyzed in acidic aqueous conditions to reverse the reaction. So non-aqueous acids, organic acids, are a better route for us here. Do you guys remember earlier in the semester, I demonstrated that we can show mechanisms this way, fully sequentially, or we can show mechanisms step by step. What I'm going to do for this reaction is show it step by step. And when we get to the acetal, I'll start to make them more fully sequential. In acidic conditions, what should be your first step? Protonation. Protonate the carbonyl. Now, do you guys have a preference on using H+, TSOH, or ACOH?
H+ is simpler.
I'll show H+ and why it's actually more confusing in the deprotonation steps. So I'll use H+, but if you're not interested in using H+, all you would have to do here is draw H, OAC, or OTS without the plus. It does, by having TSOH or ACOH, you do need an extra arrow in those deprotonation steps. You need an arrow showing the bond breaking. I'm also going to keep the alcohol in here because it's not going to be relevant now, but it is a part of the mechanism. First step, protonate the carbonyl. We now have a carbonyl that is more electrophilic so that it can react with my weak nucleophile. Second step, acyl addition. My alcohol attacks the carbonyl, breaks open the CO double bond. I would have honestly preferred to call step 1 protonation rather than protonate carbonyl, but I wanted to be specific about what you're protonating. I think you guys would agree alcohols can become protonated as well as carbonyls. So I wanted to direct the focus towards protonate the carbonyl. But if you want to get if you want to shorthand this, just think of it as protonation. Now, what is the last step? Deprotonation. In this case, we're deprotonating the alcohol that has just attacked. All right, now that is really crammed, so I'm just going to redraw that over here. Now, if you look at our acid catalyzed mechanism, you'd see that in the deprotonation step, we simply used the conjugate base of our acid to do the deprotonation. What is the conjugate base of H+? Nothing. So then what will be bonding to H+? There's no conjugate base, so there's nothing to bond with it. So oxygen takes the electrons back. That's it. We are left with our catalyst, H+. All right, now all I'm going to do is go in there and modify. If you were looking to use something else, like tosylic acid, you would just write HOTS, you'd be left with OTS minus. Here, you're still left with OTS minus because it's not playing a role yet. And then down here, OTS minus is actually bonding to the hydrogen. That's the conjugate base, and then the product would be tosylic acid again. So there's nothing wrong with using H+. It is totally correct. But it can feel a little bit more confusing if you forget what that conjugate base is. Because it's weird to think of a conjugate base being nothing. All right, now let's make an acetal, but let's have a little bit of fun with it and take a diol in this reaction. Let's take 2-butanone, react it with 1,2-ethane diol in acidic conditions. Just want to reiterate, if these two equivalences of alcohol were on separate molecules, then you would just have two different ethers, rather than having the ethers connected to one another through a carbon chain. The similarity between two equivalences of alcohol and a diol is as simple as just erasing a bond. That's it. I don't want you guys to be confused by this. I don't want you to think that it's more challenging. If anything, I think that the diols are a little bit easier. Okay, I'm actually going to do this again step by step, but if you guys want to see it sequentially, then I encourage you to do that. And I'm going to modify. I'm going to label the steps in blue and show everything in black. So first step, protonation. I'm going to use acetic acid this time. welcome to use whatever acid you like, including H+, just not H3O+. Protonate my carbonyl. I generate a conjugate base, and my alcohol has not done anything yet. Step 2, acyl addition. My protonated carbonyl is now more electrophilic, willing to accept electrons from even a weak nucleophile. Doesn't matter which alcohol oxygen attacks? No. Because they're identical to each other and they're both going to have to bond at some point. Step 3, same as last time, deprotonation. My conjugate base comes in to deprotonate. I have missed 2 things in this step. In fact, I missed something in the step before it.
Acid in the last step.
There's no acid because it's a conjugate base.
Well, when you get the hydrogen back, it would be
Yeah, here I need to show the new acid that has reformed. Good. Now the thing that's missing on the starting material and the product of this step are the same thing.
positive charge
Where?
on future ether.
Yeah. On the oxygen with 3 bonds. Future ether is a good way to think of it. The oxygen that's becoming the ether, yeah? You could think of it as the protonated ether. At this point, that's what it is. What have we just made? What functional group have we just synthesized at this point in the mechanism? That's the hemiacetal. So if you do not make a hemiacetal on your way to synthesizing an acetal, you've done something wrong in your mechanism. What comes next? What do you call this step when you what?
It's not hydrolysis, whatever you call it.
Oh, you're talking about hydrolysis?
It's not hydrolysis. You know, when you add the H or whatever to the
When you add H,
H plus or
protonation?
something. No.
Isn't that what we're doing? We're adding H+.
Over there, yeah.
But you're saying this should be the same idea, protonation, or no?
I'm not certain. So I know I want to close that, right?
Yeah. You know that at some point this oxygen needs to bond to this carbon.
Right.
But that carbon is already engaged in too many bonds. So that carbon needs to lose something in order for this nucleophile to attack it. How is it going to lose anything? It doesn't have good leaving groups. Okay, if you're stuck, yeah, I'm going to bring you back to ask what conditions you're in. I'm in acidic conditions. What do you not see in your acidic conditions right now? No positive charge. So what should you do? Protonate. Protonation round 2. What should be protonated? First of all, if we protonate this, not ideal. That just reverses our step. If we protonate this, maybe not ideal, not implausible, but not ideal given the fact that we don't want to cause any sort of possible rearrangements. In fact, what we want to do is protonate the exact same the exact same oxygen as last time. Carbonyl oxygen becomes an alcohol oxygen. Alcohol oxygen becomes protonated.
What prevents the alcohol from getting protonated?
Nothing. The only thing that prevents the other alcohol from being protonated is your work, your mechanism. And I do want to make that clear. If you run this reaction in a lab, get the flasks out, get the glassware, mix everything together, boil it, heat it. Let's say you're working with 1 millimole of reagents, 1/1000th of a mole of reagents. You have 6.022 times 10 to the 20th molecules. So that is 60 billion molecules. So what are the odds that this oxygen gets protonated? Very high. But then at some point it will also become deprotonated. And what are the odds that this gets protonated? At some point, it's very likely that this becomes protonated. So we are playing a game of statistics. We're just waiting until everything happens the way that we want it to do, the way that we want it to. What comes after protonation?
Acetal addition, or when it closes, I don't know what it's called.
Yeah, no, well, you're saying two different things. Acyl addition is when the carbonyl opens,
That's a substitution.
but there's no acyl group. There's no carbonyl that can open, right?
Right. The oxygen leaves, and then the alcohol closes in.
At the same time, this alcohol attacks and this oxygen leaves at the same time.
I would say the oxygen leaves. The water leaves first, and then the alcohol closes.
So 2 steps, SN1, if you will. Actually, that
would be my guess.
SN1 would make sense given what we learned in OChem 1. This is a good leaving group, but it usually leaves a carbocation. And this is a weak nucleophile, so it doesn't normally attack unless there's a carbocation. So a carbocation is not a bad idea. The thing about this step, though, is that the carbocation that can form is not a normal carbocation. If this group leaves, and I'm going to keep my conjugate base in here, ACO minus. If this group leaves and it creates a vacancy on this carbon, oxygen has a lone pair that it can donate in. Do you know what that looks a lot like? A group leaving while a double bond forms? That's elimination. However, if you don't really see it as elimination, or if you'd like to see it in another way, I have another way that you can think about this.
That's a substitution instead.
So first of all, there is a resonance form that has a carbocation. but that's not a major resonance form because it doesn't have complete octets. What does this functional group look like to you?
No functional.
Sure, none that you're used to. There's an alcohol on there, but talk to me about the other oxygen. Doesn't it look like a carbonyl? And it looks like an ether. You could call this the formation of the alkylated carbonyl. That's how I like to think of it. It's a carbonyl that has an alkyl group on it. Sorry?
Carbether.
A carbether. There you go. You see, we've got better ideas of how to name stuff than IUPAC does sometimes.
Doesn't take much.
All right, now that we have this alkylated ether, and I want to draw you guys back because I'm giving you a mechanism with a diol, but the mechanism with two equivalences of alcohol is exactly the same. Remember I said it's the difference of just erasing a bond. If I was working with just methanol here, two equivalences, I would just erase this bond. If I was dealing with two equivalents of methanol, I would just erase this bond. I still have an ether, I still have an alcohol, they just aren't attached to each other. I still have an ether, I still have an alcohol, they just wouldn't be attached to each other. Now at this point, when I form my alkylated carbonyl, so pulling you back to this point, this is a protonated carbonyl. The difference between a protonated carbonyl and an alkylated carbonyl is that instead of O bonding to H, O is bonded to an alkyl group. If I had two equivalences of alcohol, I'd just have one R group coming off of the carbonyl, and I'd have an alcohol in the molecule as well. So what do you think happens in this step? Keep in mind, it's very similar to this.
So acid takes hydrogen.
No.
And
No.
No?
No.
Do we need another molecule of that?
What?
Of the diol?
We don't need another molecule of the diol. No.
So then the two electrons from the OH are going to attack the carbonyl.
Acyl addition. Exactly. And as the reminder, if you didn't have the diol, it would have just been a second equivalence of an alcohol attacking. But because it is a diol, the second equivalence is attached to the molecule. So this is where we get our ring. What came after acyl addition last time? Deprotonation. Conjugate base deprotonates the newly formed ether, and it leaves me with my acetal and my conjugate acid. Now I really do try not to make things more confusing than they need to be, but I really am trying to emphasize the fact that a diol acetal formation and two equivalences of alcohol acetal formation are very simple. So imagine instead of 1,2-ethane diol, I had 2 equivalences of methanol. Would you agree that I could just write it as that? CH3OH, CH3. It looks a little weird to draw methanol that way, but I could, which means all the way throughout this mechanism, here's my ether, here's my second equivalence of alcohol. Here's my hemiacetal, ether, alcohol, and here's my second equivalence of alcohol. Same thing down here. Once this gets protonated, I form my alkylated carbonyl. This is now just OCH3 instead of the diol, and I have my second equivalence of alcohol. Same thing here. Same thing here. They're just no longer connected to each other. So, in my opinion, it's actually easier to show the mechanism for the diol because you don't have to draw 2 equivalences of an alcohol at each step in the mechanism. You just draw that one molecule and it has both equivalences of your alcohol. But in terms of logistics, are the arrows any different? Are the steps any different? None whatsoever. Everything is exactly the same other than the 2 alcohols not being connected by the same carbon chain. You guys okay with that? So here's a word to the wise. So many students lose points on this mechanism on both the unit test and the final exam. There's no need for it. If you can just write down these 7 steps, you wouldn't even need to have a mechanism example. However, if you're going to have a mechanism example on your cheat sheet, make sure that it has 7 steps. And the reason that I say that is because other resources who are not the professor who will be grading you, which is me. For instance, the online textbook that I do like to reference from time to time. When they show the mechanism for acetal formation, they're going to give you steps like proton transfer. I guess they actually don't do that here. There are many mechanisms though that this textbook does that just says proton transfer rather than saying deprotonation followed by protonation. They just say proton transfer. It's less likely, and this is more likely. This is more plausible. 7 steps. It's kind of a lot. That's what we look at. Any questions? That took a whole board. However, that's only because I did it step by step. If I actually showed this fully sequentially, this is how much space it would have actually taken up. Repeating the reagents at every step. Oops, that was the one thing I needed to keep. Repeating the reagents at every step, it really takes up a lot of space. Wouldn't you agree? That's not that much board space. But it's really hard to see what is happening when every single step has arrows all over the place. So figure out what's best for you. Maybe when you practice the mechanism on your own over the weekend, you do it step by step by step until you recognize every step. And then you try to do it from scratch, fully sequentially. All right, now I want to briefly look at the similarities that we have here with the imine, the enamine, the oxime, and the hydrazone. We're not going to look at each of them. Instead, we're going to look at just one of them and recognize that the only difference is what's on the other side of the nitrogen. So let's take acetone. Let's react it with methylamine in acid, and we'll generate this methylamine, and of course a byproduct of water. Now, rather than going through step by step and showing the arrows, what I want to do is just look at the major intermediates. We can predict what's going to happen without needing to show all of the arrows. What should happen in the first step? Think about what type of conditions you're in. Good. In acidic conditions, our first step is protonation, which means at the end of the first step, I should have a protonated carbonyl and my methylamine. I do want to point something out. Nitrogen is a better base than oxygen. So in this mechanism, it requires a state where the oxygen has become protonated and the nitrogen has not. What are the odds of that happening? Not very good. So you're really going to have to give this reaction a lot of energy in order to create a situation where the bad base is protonated and the good base is deprotonated or non-protonated. What would happen after the protonation step? Acyl addition. Now in this acyl addition, much like the last two, the nucleophile is going to have this positive charge. What comes next? Deprotonation. What's going to be deprotonated? The oxygen or the nitrogen? Right, the nitrogen, which has the positive charge. Now, we stopped here in the acetal formation when it was oxygen attacking, and we said that this would have been called the hemiacetal. So maybe we could call this the hemiamine. I like how that sounds. The hemiamine. What happens next? Protonation. Nitrogen should become protonated. Get the alcohol protonated. That needs to be my leading group. What happens next? I shouldn't have erased all of it. That's my bad. Here, in this textbook, they actually referred to it as dehydration. Yeah, you guys know that dehydration is just a specific type of elimination. So my elimination by removing the water means that nitrogen makes the double bond. In our acetal mechanism, this was the alcohol that made the double bond, or I should say, the newly formed ether. But nitrogen is replacing the oxygen in this mechanism. what would be the last step in forming my imine? Just deprotonation. And look what we have there. The final product. All right, now just quickly, what I want to show is how the formation of the enamine differs just at the last two steps from the formation of the imine, the oxime, and the hydrazone. So this time I have dimethylamine, NHCH3 Remember that I cannot form an imine because my nitrogen doesn't have enough hydrogens to give away now. So all the steps 1, 2, 3, and 4, they're going to look similar. Protonate the carbonyl. Nitrogen attacks and takes on a positive charge. Nitrogen gets deprotonated, oxygen gets protonated. Now at step 5, it still looks similar, but you'll notice that in step 5 with the imine, the oxime, and the hydrazone, my nitrogen has an H. And just like you guys said, this is just going to go through deprotonation where the nitrogen takes the electrons back from the hydrogen. Gives me the imine or the oxime or the hydrazone, depending on what's connected over here. In this secondary amine, there is no hydrogen to give electrons back to nitrogen. So nitrogen needs to get electrons back, and it can only do that by taking from the pi bond. I think you guys would agree that that's not a deprotonation step. All that's going to do is leave a positive charge on the carbon. So then one of these adjacent carbons gets deprotonated instead. That allows nitrogen to go back to neutral. It allows for the deprotonation step to occur and make things neutral. The thing is, the deprotonation step can't occur from anywhere else. It has to occur from one of those carbons. I can hear somebody in my brain saying, could I deprotonate from one of these carbons? But if I deprotonate this hydrogen, or this carbon, and I give this electron back, yeah, it breaks nitrogen's octet. So really, the only place nitrogen can get this lone pair back from is the pi bond. So I need to give that pi bond back to nitrogen, and that helps me confirm where the hydrogen needs to be taken from.
In the case that those other two R groups don't have, for some reason, hydrogens.
Well, it wouldn't matter. Wouldn't matter. Oh, you mean these two R groups?
Yeah.
Yeah. What would happen then?
Nothing.
You get stuck.
Or would you keep going until you find hydrogen somewhere?
Okay, so I think you've got an interesting thought, which is, what if I have these aromatic rings? And these positions on the aromatic rings, they don't have any hydrogens to be lost so that they can form a double bond. So you would get stuck here.
Or wouldn't that be conjugated?
Conjugated, sure.
That means that
But-
there is a bond already.
Okay, like a partial bond, a partial double bond. But there's no elimination that could be done. If you wanted to look at it like this, I want to take this hydrogen away so that I can give electrons back to this nitrogen. That would mean forming a triple bond in the ring. That's not unheard of. That's called a benzyne. But actually, I don't want that to be in the ring. I want it to move through the ring so that I can put this electron pair back on the nitrogen. Now that is unheard of. That's an sp carbon that's sitting there with 120-degree bond angles. So that's not going to form, which means nitrogen isn't going to be allowed to take on those electrons.
So you just stay with your, what do you call
I mean, that would be more stable than the original.
I think actually I was a little bit mistaken. I should have been deprotonating from this carbon to form that, to push these. So what I'm saying is the activation energy to do any sort of elimination step here would be incredibly high. The activation energy would be so high, you'd probably just destroy the compound before you actually ran an elimination step. But, what was I going to say? Oh, this isn't inherently unstable. Nitrogen takes on positive charges all the time. Think of ammonium. Ammonium hydroxide, super common salt and salt solution, base solution. Ammonium hydroxide has a positively charged nitrogen. So you would probably end up isolating this iminium. Iminium.
But how is it unstable? Wouldn't it be more stable because each ring has a resonance or a conjugation?
Okay, well, I'm saying like this might be more stable than if you had a tert-butyl group, because the tert-butyl can't conjugate, but the rings can conjugate. I'll give you that. But there's no way to finish the reaction and get to the enamine. If these two groups don't have hydrogens to run elimination, you're done. Or, sorry, not elimination, deprotonation. Although it does feel a lot like elimination. I don't think I've satisfied you, Rob. Okay. Now let's see if that's a real word, iminium. Hey, do you see how there is some good in the world?
anything?
Iminium, a protonated imine.
Oh wow. There you go.
See, that's nomenclature doing its job. That's nomenclature being systematic. I don't think that I've, maybe I have heard of that name before. It wasn't something that really called to me. Yeah. I think if they said it anywhere, they'd say it in here. Oh yeah, there it is, iminium ion. Okay, this does raise a very important question. Yeah, okay, I did. When we reviewed reactions with aldehydes and ketones, I gave you the Wolff-Kishner reduction in our review. And now that we are looking at reactions with aldehydes and ketones in the presence of hydrazine we can better understand the mechanism of the Wolff-Kishner reduction. So here, if what I had was H2N NH2, I'm going to end up getting to these imine structures. So here's my imine, but because it's hydrazine, it's imine with an NN bond instead of a nitrogen to hydrogen, nitrogen to carbon, nitrogen to oxygen. And that allows for this resonance. Look what happens in this resonance. It puts a negative charge on carbon, which makes it basic to take on a hydrogen. And then once again, this group kicks off, giving a lone pair to carbon, producing N2, which allows it to become protonated. I just want you guys to think about how bizarre this is. Carbon rarely takes on negative charges. But in the hydrazine reaction, the setup allows for carbon to become far more nucleophilic than you would expect it to be, far more basic than you would expect it to be. How do you take a carbonyl carbon, where the carbon is always partial positive, and how do you make that carbon partial negative to become an alkane? That's the beauty of the hydrazine reaction. We're not going to look at that mechanism, but would you agree that that mechanism is no more challenging than the mechanisms we just looked at? So, once again, one of my philosophies in teaching this class is I'm going to give you the mechanisms that I want you to master, because I feel that if you can master the mechanisms I give you, you can predict any other mechanism. You'll start looking for resonance. You'll start understanding where charge should be placed. You'll start understanding what steps should happen after what steps. And I want you to really master them. I don't want you to just memorize a bunch of things and not have any mastery at all. Now, before we move on, I just want to say the reverse reaction of the acetal and hemiacetal. It's exactly the same steps, but in exactly the opposite order. I think that I do want to give you guys an example of that hydrolysis mechanism, because on the exam and on the unit test, you may see one, you may see the other. I'm going to do hydrolysis of acetals. The hydrolysis of imines, pretty much identical. For reference, our carbonyl to acetal mechanism was protonation, acyl addition, deprotonation, protonation, elimination, acyl addition, deprotonation. PAD-PED. That was to go forward. If we want to go backwards, our first step needs to be protonation, followed by elimination, followed by addition, followed by deprotonation, followed by protonation, followed by elimination, followed by deprotonation. What I'm doing here is connecting every step with its opposite. If the forward mechanism had a protonation step, the reverse mechanism has a deprotonation step at that same point. If the forward mechanism had an addition step, the reverse reaction has an elimination step at that same point. Now, we'll go through this pretty quickly. I'm going to take this 1,1 diethoxy cyclohexane. Oops. I'm going to hydrolyze it with H2O and H3O+. And I'm going to show this fully sequentially. The first step in my reverse reaction is protonation. Take one of those ethers and protonate them. Once again, I'm going to show every reagent as it's needed. Or sorry, I'm going to show every reagent throughout, not just as it's needed. First step, protonation. Second step, elimination. That means I'm going to kick off my newly formed alcohol, and I'm going to use the second ether to form that alkylated carbonyl. Is that intermediate too small? Should I redraw that for you guys to see it better? This one. Now that I've done elimination, I need to do addition. This time, addition happens from water. After addition, I need to run deprotonation. That water that just attacked needs to be deprotonated. After I deprotonate the water, I need to protonate the ether. I need to make this ether into a good leaving group. Oops, one step too far. Now that I've protonated the ether and made it a good leaving group, I'm going to run elimination. The alcohol reforms a carbonyl, kicks off the ether to be an alcohol. And in my last step, I need to deprotonate the carbonyl, reform my regular carbonyl, and reform my catalytic acid. I know that's a lot to follow, but did you see how each step predicted what happened next. Each step was exactly the opposite of the acetal formation. Protonate the acetal. Eliminate an alcohol. Attack with water. Deprotonate the water. Protonate the other ether. Protonate the hemiacetal. Eliminate the second alcohol. Deprotonate the carbonyl. And you're back to your final product. Our forward direction was protonate the carbonyl, acyl addition with the alcohol, deprotonate the alcohol, protonate the water, do elimination, attack with the other alcohol, and deprotonate it to the final acetal. Okay, when you guys are ready, we can take a short break or we can just keep hauling through.
Wait, I'm a little confused.
Okay?
But as a
Yeah? What did you think you missed?
I didn't realize that which alcohol was living on the first step here from the bottom.
Hmm.
Yeah, so that one's living, so it's the one on the right that is forming the double one.
This one here
Yeah.
forms the double bond, leaves.
Yeah.
Yep. Good. Do you guys need a break? No. Okay. Let's review some ways that we can make carboxylic acids. I'll just take, for example, here benzoic acid, and I'm going to give kind of a flow chart showing a lot of different ways that we can synthesize it. One of the oldest methods that we have for synthesizing carboxylic acids is by oxidative cleavage of alkynes. Take an alkyne, cut the carbons from each other, both sides will be carboxylic acids. Now, in the event of this alkyne, a terminal alkyne, one of the carboxylic acids that forms is carbonic acid, which just bubbles away as carbon dioxide. Then, this semester, we saw that we could make carboxylic acids by taking carbon chains at the benzylic positions and oxidizing them, for instance, with chromic acid or hot potassium permanganate. Then we saw that we could make carboxylic acids by taking primary alcohols and oxidizing them with our strong oxidizer, chromic acid. And more recently, we saw that we could take aldehydes and use chromic acid to turn those into carboxylic acids. Now, the only new way that I have yet to show you to synthesize a carboxylic acid, it's actually one of my favorite ways to show the synthesis of a carboxylic acid. If I have a Grignard, a strong nucleophile, then I can introduce carbon dioxide, which acts as an electrophile, a 1-carbon electrophile, and it opens to form a carboxylic acid. So of course, I'm using just a generic example where I have benzoic acid. So my Grignard needs to be phenyl Grignard. And when phenyl Grignard attacks carbon dioxide, it forms that carbon-carbon bond, leaves me with a carboxylate that then gets protonated into the carboxylic acid. I want to highlight, for example, why this is different than using our other 1-carbon electrophile like formaldehyde, where here an organometallic attacks the carbonyl carbon but breaks open the only carbonyl carbon. Breaks open the only carbonyl double bond. Carbon dioxide has 2 carbonyl double bonds. So you can break one of them open and still preserve the second one.
Okay, so could you do that with the first one with a Grignard, but without some of the thing.
Yes,
So any organometallic would do it.
not cuprates.
Is it okay?
But remember that organolithiums and organomagnesium halides, the Grignards, basically interchangeable.
Okay.
Yep. Anytime you see a Grignard being used, you can use an organolithium. Anytime you're using an organolithium, you could use a Grignard. Logistically, it's a lot easier to work with magnesium because it doesn't explode when it reacts with water. Lithium, on the other hand, violently reacts with water. So it's a little bit more dangerous to work with. Okay. The other thing that I want to show you is I just want to remind you how simple it is to synthesize a nitrile. For example, let's say that I want to make acetonitrile, CH3CN. This can be done with simple SN2 substitution. Take cyanide, react it with an alkyl halide, substitute. Now you have a nitrile. Okay, what I have for us next, I'm actually going to show on the screen as well because I think if I give you an idea of what it will look like, it might help you format it in your notes better than just going off what I put on the board. So in this carboxylic acid derivative PDF, got two different flowcharts, two different graphics. Let's see if I can actually show it this way instead. So what I've got here is a connection between all of the different carboxylic acid derivatives, acid chloride, ester, amide, nitrile, and the acid anhydrides. And then in the center, I've got the carboxylic acid. In blue are hydrolysis reactions. Each of these compounds, acid chloride, anhydride, nitrile, amide, ester, each of these can be hydrolyzed in blue back to a carboxylic acid. Some of them require different conditions. You'll notice that the acid chloride can be done with water and acid, whereas the stronger carbonyls, the nitrile and the amide, they actually require harsh conditions. They require strong basic conditions followed by an acid workup. Then in red, we've got these reactions that take us from the carboxylic acid to each of the derivatives, except for the nitrile. Carboxylic acid cannot directly be converted into a nitrile, but I am going to show us a way that we can indirectly convert that. Now the other graphic that I have shows the relationship between all of the various derivatives. The acid chloride can be converted into an anhydride, or into an ester, or into an amide. The acid anhydride can be converted into an ester or an amide, but not to an acid chloride. And there is a connection where the ester can be converted to an amide, but not in reverse. It's just not very common to use it, so we're not going to see it done this semester. Instead, it's far more common to take any derivative that you want to change into another derivative and somehow convert it back to an ester and then back to a carboxylic acid, and then from the carboxylic acid to an acid chloride, because from the acid chloride you can go anywhere. As a reminder, acid chloride is the most reactive carbonyl. So it can easily be converted into any of the less reactive carbonyls. The anhydride, second to most reactive carbonyl, can be converted into anything that is more stable than itself. That's the same reason why the ester can be converted into the amide, because the amide is more stable, but none of these reagents can go from more stable carbonyl to less stable carbonyl, except for in the event of hydrolysis to the carboxylic acid. Now, the way that I'm actually going to lay out this graphic is kind of a mashup of these two graphics here. So I'm going to have my carboxylic acid here, and I'm going to show my acid chloride. Down a step and over, I'm going to show my acid anhydride. Down a step and over, I'm going to show my ester. Down a step and over, I'm going to show my amide. And then down a step and over, I'm going to show my nitride. And we're going to have lines that convert us between each of these reagents and the carboxylic acid, and then lines that convert us from a more reactive reagent to a less reactive reagent when we have them. I'm going to start by adding in blue arrows that will show me my hydrolysis process for each of these reagents. I want you guys to keep in mind that any reagent that can hydrolyze the least reactive carbonyl can hydrolyze the most reactive carbonyl. So I'm going to give you guys a spectrum of reagents that will actually hydrolyze here. The acid chloride will hydrolyze just in the presence of water. So if you have acid, H3O+, or if you have base, hydroxide, that will also hydrolyze it, because acids make carbonyls more reactive, bases are always more reactive. But you can hydrolyze acid chlorides and anhydrides using just water. The esters, however, require stronger conditions. Esters require acidic conditions in order to be hydrolyzed. To be fair, you can also run it with base and then acid afterwards. That works just as well. And the amides, these generally are not reactive enough in acidic conditions. They require a strong base to hydrolyze them. But of course, you can't form a carboxylic acid in base, so you need to have an acid workup afterwards. The nitrile, likewise, requires a strong base to hydrolyze it, followed by an aqueous workup. One reaction that Some see in OChem 1, I think I've hinted at it a couple of times this semester already, the conversion from an acid chloride, the conversion from a carboxylic acid to an acid chloride requires thionyl chloride, SOCl2. The conversion of a carboxylic acid to a symmetric anhydride requires P2O5. P2O5 is referred to as a dehydrating reagent. Its job is to help pull water out of the reaction. And you can see that two equivalences of carboxylic acid come together, less a molecule of water to make the anhydride. The ester is generated from a carboxylic acid when an alcohol and acid are present. We've already seen this reaction in our section 18 on alcohols. Tomorrow we're going to look at the mechanism for this reaction. The synthesis of an amide from a carboxylic acid also requires a dehydrating reagent. But this time we're going to use something called DCC. I can never for the life of me remember what DCC stands for, but I can draw it. N-dicyclohexyl carbodiamide. If we get time, we'll look at it tomorrow. But all you need to know is that this helps pull out H2O from the reaction so that it doesn't. It's allowed to go forward. So keep in mind, I've got NR2 here, which means that I need NHR2 as a reagent. Like I said earlier, there's no reaction that takes the carboxylic acid to a nitrile, but you can take an amide if R is equal to hydrogen, as long as this is a primary amide, NH2. You can use P2O5 to dehydrate the carbonyl. You'll remove H2 and O, and you make the nitride. Now, we're also going to look at all of these across reactions. So to take an acid chloride to an acid anhydride, what I need is to substitute the chlorine with a carboxylate group, a carbonyl with an O-. So here I require just a simple carboxylate. In order to take the acid chloride to an ester, I need to have an alcohol that matches the ester linkage. At some point, I will also need to deprotonate the oxygen of the alcohol to be left with my normal ester. However, chloride is not a good base for any sort of deprotonation, so we also require pyridine in this reaction. I'm abbreviating pyridine as PRY, but this is an organic base. It's that aromatic compound. And it acts as a good base for deprotonation. In my last conversion from the acid chloride goes to the amide, and what I need here is whatever amide I want to make, and I need it in excess. I don't need to add pyridine like I do with forming the ester, and that's because an amine is just as good of a base as as pyridine. So if I just add excess amount of my amide, I'm good to go. The other conversions here are actually very straightforward as well. The anhydride can utilize the same reagents, alcohol and pyridine, to form an ester, and the anhydride can use an excess amount of amine to form the amide. To be fair, the ester can also go to form the amide with the same reagents. We're just not going to see it. It's just not as common. What do you think? It's just a block of reactions. It's just a bunch of reagents. What we need to do tomorrow, we need to look at reduction of all of these groups. That's not going to take very long. We need to look at the mechanism for esterification, forward and backwards. That's not going to take very long. It's actually shorter than the acetal mechanism. And we need to try and apply synthetic schemes to these reactions. Maybe the only other thing that we need to talk about is the difference between synthesizing a symmetric anhydride and an asymmetric anhydride. So we've got our work cut out for us tomorrow, but we're in the clear. You might even be able to start making a guess at your homework for the carboxylic acids and nitrile, or carboxylic acids and derivatives section. But for sure, by tomorrow night, you guys will be able to finish those up. Okay, have a great day, guys. Happy studying.